Greetings, welcome to Lab 5, Part 3 on hypothesis testing. So we're going to go ahead and work on problem 4.26 in this particular one. So let's scroll over, excuse me, not 4.26, this is 4.28, yes, 28, okay. So in 4.28, we're asked to take a look at testing for food safety. So if we're testing for food safety, what they want to know for us is they're saying is a food safety inspector is called upon to investigate a restaurant with a few customer reports of poor sanitation practices. Nasty. The food safety inspector uses a hypothesis testing framework to evaluate whether the regulations are not being met. If he decides the restaurant is in gross violation, its license to serve food will be revoked. So write out the hypotheses in words here for us. Okay, so what are the null and the alternate hypothesis in words? Well, the null hypothesis says that what? There is no sanitation issues, right? Or how about there are no? Issues, the food is safe, right? So that would what the null hypothesis would be say. You think about it this way, it's just as if we were working in a court case. We're going to presume that they are innocent unless the evidence indicates otherwise. In other words, you're presumed innocent until proven guilty. So that would be the same thing that the health inspector should take, or the food safety inspector should take into account also, okay? All right, so there are sanitation issues. Sanitations, oops, my bad, I misspelled it almost twice here. There are sanitation issues. The food is unsafe. Montezuma's revenge will rain upon all who eat here, okay? So what is the type 1 error in this context, okay? Well, let's remind ourselves real quickly what type 1 error is. Let's just do the definition of that first. So type 1 error. What is type 1 error? Well, type 1 error is rejecting the null hypothesis when in fact it was true. In other words, we falsely reject the null hypotheses, okay? So what is it in context here? So we would reject that there are no sanitation issues, right? When in fact that was true, right? So what that says is we reject that the food is safe to eat when in fact it is safe. Okay, so what would a type 2 error be in this context? So let's go again, same thing, let's define what type 2 error means. So what is a type 2 error? Well, a type 2 error is when we fail to reject the null hypothesis when it is false. I understand what that means, but I find the double negation sometimes annoying. But we can think about type 2 error very similar to the way we think about type 1 error, and that in this case we're rejecting the alternate hypothesis when it's true. So in other words, if we approach it with exactly the same way that we approach type 1 error, many times that makes it easier to understand what you're doing. So we reject the alternate hypothesis when in fact it was true. So notice these are both mistakes. They're mistakes we don't want to make, but they are inherent into hypothesis testing that we don't have 100% certainty, is that there is a chance of us making a mistake in rejecting the null or in rejecting the alternate. The probability of rejecting the null hypothesis, by the way, is given by alpha. The probability of rejecting the alternate hypothesis, in fact, when it was true, or making a type 2 error, that's given by beta. Okay. All right. So what would in context, what would that mean in a type 2 error? Well, let's think about it. That means that we rejected that the food is not safe to eat when in fact it is not safe to eat. So that's bad, right? In other words, a type 2 error here means that we said we rejected that there are sanitation issues and the food is unsafe, when in fact that was true. That was the truth of it. And we rolled with or supported the null hypothesis that there was no sanitation issues. So which error is more problematic for the restaurant owner and why? Okay, so of these two errors, type 1 error is a bigger problem for the restaurant owner. Why is it for the restaurant? Well, he would get his license, or he or she, revoked, right? Okay. When in fact he was serving safe food. That would be a drag for him, right? Okay, which is a bigger problem for us diners? Well, for us, it's a type 2 error, right? They'd say, oh, this place is just fine, no worries, and then go home and discover that I have food poisoning. We would get nasty results from eating there. That's one way of thinking about it, right? In other words, that it's not a very good situation for us because we would end up possibly getting food poisoning or maybe even worse, okay? All right, and then last but not least, they say, as a diner, would you prefer that the food safety inspector require strong evidence or very strong evidence for the health concerns before revoking the restaurant's license? Explain your reasoning. And we would go with strong evidence. We're going to go over to the whiteboard here in just a minute and explain this a little more. And the reason for that is it's the relationship between type 1 and type 2 error. We want to make alpha equal to, let's say, roughly 10%. We want to make the chance of type 2 error as small as possible. And the type 2 error, just so we know what that, remind ourselves, that's beta. Okay, so I want to go back over to the whiteboard for just a minute and talk about why I came up with that particular statement there. So let's do that real quick. So let's get back over here to the whiteboard. Let's get a blank sheet. And it has to do with the relationship between alpha and beta. The way alpha and beta work is as follows. Let's pretend for just a moment. I'm going to make a quick drawing here. Wrong tool there. There we go. Let's make a quick drawing, and let's say that this was the distribution of the null hypotheses. So this is HO. And let's say down here that this is the distribution of the alternate hypotheses, HA. And let's say, for all intents and purposes, that we decided to do a left-sided test. And so this region that I'm going to shade over here, this region is going to be alpha. And so that's my probability of making a type 1 error there. So remember, alpha is the probability of making a type 1 error. So recall that if our value falls into this region right here, then that means that we would reject. We would reject the null hypotheses. And any value that fell over in here, we would accept the null hypotheses. Well, let's assume that we're on the same scale between the null and the alternate. In other words, that these horizontal lines are on the same scale number line wise. And let's transfer that value down here to the alternate hypotheses. Well, notice that in the alternate hypotheses, that this region right here, let's go ahead and we'll shade that in kind of a bluish sort of color, that this region right here is going to be where you reject the alternate hypotheses. Why? Well, here, hang on for just a second, see if this makes sense to you. Back up here I said that this right here is where I rejected, so this would be what? Where I failed to reject. I'm going to write except for the moment, but that's failed to reject, okay? Well, notice that if I'm rolling with supporting the null hypotheses, that must have meant that I rejected the alternate hypotheses, so that's reject down here. And so the thing to see is that that blue region right there, that's beta. All right, now why did I want to do this drawing here? Because what I want to show you is the relationship between alpha and beta. Notice that is if I move this line this way, and I move alpha over to here, okay? In other words, if I make alpha bigger, if I shade a bigger region for alpha, notice what that does to beta. Is that it comes over here and it shrinks beta, doesn't it, right? We need to erase some of beta here, because what that did is that moved the line over to the right some, and that ended up making beta smaller, didn't it? And it's by increasing alpha, I make beta smaller. As by decrease alpha, I make beta bigger. So the punchline is this: as alpha gets bigger, beta gets smaller. As alpha gets smaller, beta gets bigger. That's the relationship between alpha and beta. As you increase one, the other one decreases. Now, the only mitigating factor, the only thing you can do to make them both shrink, you can shrink them both by increasing n. You can reduce the probability of making a type 1 and type 2 error by making n bigger. And what I mean by making n bigger? Well, that means making a larger sample, right? So if I take a larger sample, then I'm going to have more information, and having more information means that there's less chance of me making a type 1 or type 2 error. Okay, so let's go back to RStudio and let's go type some of that into my RMD here, okay? So we have strong evidence, or we want to use strong evidence, not extremely strong evidence, because we want to try and make alpha small so that we don't make beta too, and we want to make alpha bigger so that we don't make beta too huge. In other words, if we make alpha bigger, beta is going to get smaller, okay? We want to have safe food, okay? Now that's almost counterintuitive, but notice we want to make sure that we reduce the chance of type 2 error. That's the main thing. Okay, cool. Make sure that you've got the definitions of type 1 and type 2 error in your reference book. We will definitely be particularly referencing type 2 error. Excuse me, not type 2. We will not be referencing type 2 error. We'll be referencing type 1 error fairly often, so make sure you got that definition down.